I think we're going to try to get started. Hopefully everyone has been able to get some lunch. Thank you all for coming over on a fairly rainy day. It's always hard to predict the outcome when it rains. So I'd like to welcome you all to the Wilson Center. My name's Dave Rajewski, and I direct the program on science and technology innovation here. And also I'd like to welcome Mike Rocco, who's the senior advisor for nanotechnology at the National Science Foundation. I was thinking back just on the sort of trajectory of the NNI, and it goes back obviously to a little over 10 years now. Actually, the work on nano started earlier. But when you begin to think of it in political terms, it's gone through 3 presidential elections, numerous shifts in the Congress in different directions, significant changes, wholesale changes in the staff at the White House Office of Science and Technology Policy. And it's still going very strong. We're looking at cumulative investments of over $12 billion now. And I guess this year's budget or coming budget is $1.8 billion. So I think it's a testimony to the work that a lot of the people in government and industry and academia have done. But I also think it has a lot to do with Mike. There's one consistent person going back probably 10 or 15 years now that's been invested in pushing nanotechnology, and that's been Mike Rocco. And I think one of the interesting things that Mike's done, which I think is kind of a model maybe for other areas, is that he's constantly been asking the question, where's the field going? Where's it come from? Have we gotten where we thought we would get in a certain amount of time? And if we've gotten there, do we want to change direction? And what are the implications of changing direction? And I think that conversation has been had numerous times. There was obviously a lot of that discussion early on as the NNI was forming, and Mike's gone back and sort of after a decade or so kind of revisited that set of questions. He's tended to do it, I think, in a fairly open way with a lot of people from industry, but also internationally. And I think that's one of the interesting pieces of the conversation. I remember sitting, I think, in your office in 2005, and we had this discussion about let's get everyone together that's running a nanotech initiative in the world. And I think at that time, when we had the meeting in Arlington, it was, what, 20?
Yes, 26 countries.
26 countries in the EU. All in one room for 2 days in Arlington to have a discussion about nanotech globally. And I think Mike's just run a similar exercise going around the world and meeting both here and in Germany, and then also in Japan with over 250 people. So I think that's been part of, I think what's made this fairly successful is the kind of openness of the discussion around, what are we doing, where should we go, what are the research directions, how do we address some of the implications. So this is, I guess, the shorthand term for this version is Nano 2, the next 10 years. And so I'd like to introduce Mike Rocco, and Mike will take you through kind of the results of, I guess, 1.5, 2 years of discussions now globally to try to come up with some new research directions. For those of you watching on the web, we'd also like to include you in the Q&A. So if you've got questions, at any point in time, feel free to send them in just to nano@wilsoncenter.org, nano@wilsoncenter.org, and if we're lucky, they'll appear on my device here, and we can take those questions after the presentation. So, Mike?
Thanks, Dave, and I'm grateful for your invitation to speak at Woodrow Wilson Center. And I like, first of all, to recognize that Woodrow Wilson Center is independent observatory where important ideas can be presented, and I think I will try to be in that line of your mission, and I will try to show in brief several things. How this now is seen as a mega trend in science and engineering was born, what are the main results in the last 10 years, what are the real advancement, and what are the opportunities for next 10 years by considering what will be the societal needs in next by 2020. And I will speak certainly by using my experience in different international contacts with in establishing coordinating NNI, at least in the first 6 years. And also we have input from about 250 leading experts from 35 countries. I will like to, first of all, to mention that nanotechnology has remained on the top of the wave of discovery and innovation 10 years, which is a long term for a new field of science. And we estimate that this will continue for another 10 years when there will be mass use of nanotechnology by 2020. Now there are about $15 billion spent for research and development in this field. What is more important, in 2010, we have a change of direction, which is mainly caused by the level of scientific development. What happened, we moved from indirect measurements and empirical methods to synthesize components to be used in products to be improved. We move now to direct measurements, science-based method to synthesize and manufacture systems that eventually will generate fundamentally new products. That means it's a qualitative trend, change, and this change has to be captured in a format that the community will understand and will see the future in this. It was a kind of loss of momentum in the last 2-3 years because people were still looking to the targets set up 10 years ago. Another point that I will make during my presentation is that as nanotechnology is becoming a general purpose technology for all material and medical world and will be mass used in 10 years from now, it's more important to have a different governance, including to institutionalize nanotechnology. What means this? Now we do by ad hoc projects. For instance, at NSF, we established several centers for 5 years and we close them. Well, this is not an approach that is the best suited if it's a mass use and is a continuing development in the field. That means it has to be institutionalized to create programs in manufacturing, in research, in medicine that have a continuity in environmental health and safety, and are no longer ad hoc, and so has to be a different kind of governance. First of all, how we started. That means to look for 10 years ahead, we started what are the earlier signs of change? What are the breakthroughs now that in 10 years will be eventually in technology? We look what will be the needs by considering the population change. Population means number, means change of wealth from west to east that was massive in the last 10 years. We look to new emerging technologies, and that means we look in all this context. And we reach a conclusion that basically now we have 3 general purpose integrating technologies. One is nanotechnology for material world, one is information for communication and called computation, etc. Another is complex systems approach that is still in development and can be applied for different areas. If you look now in US, nanotechnology initiative has particularities. First of all, is the only one that is mainly justified by science as a beginning and was established on a competitive basis. That means we have about 30 ideas. When Clinton has some surplus in 1999, and it was a selection process, and was science motivated to tell we have the science and it's so important that in 10-20 years will have a strong impact on economy. All other projects that you see were caused by external factors like Apollo program, like AIDS, like Sematech, that in that case, industry was already established. On Apollo was an international competition. On Manhattan program was the war. Or in environment are international agreements. That means this initiative also has a particularity. It was organized from bottom up. That means it was not in a fixed amount from top down, but was based on competitive basis, developing projects to be competed. And the goal was to have a general purpose technology. And we started like a science project. What means this? We redefined nano. That means one part of the success of nanotechnology initiative is that up to 99 were only definition for based on size and for a specific field. For instance, in Germany, it was ultra precision engineering. In Japan, or electronic devices on surfaces. In Russia, was ultra dispersion. And none has this general concept that nanotechnology, in fact, is because you are a transition between single atom, single molecule, to bulk behavior, where all fundamental properties are established, the life is established, manufacturing can be done easily. In fact, if you go back in histories, after the Big Bang, initially was a coagulation, form atoms. If we would not have the next phase of forming nanoscale, we have only fixed properties of 100 atoms, maybe 20 more frequent. Would have been no life, no diversity. That means all this diversity in life is caused by this nanoscale, this assembling that we still don't understand why this assemble. In a structure, all the time is between 1 and 20 nanometers that gives the macroscopic properties. And now what is interesting, we arrive to a level that we can make intervention and understand that level. And so, and our definition is not specific for a field, it's control of the nanoscale. That means we have only one nanotechnology. And this was a point that was done, we done in similar way, we went in 20 countries in 98, 99. And basically, the result of this definition that has a unifying concept and also a transformative concept has to be based to exploit new phenomena, new properties, and to lead to restructuring, to have ability to restructure nanoscale. Also, we have this developing a 10 years vision that what is interesting, maybe to tell something that will be surprised, after 10 years, ISO, after long debates, arrived to exactly the same definition that we have 10 years ago. If you go and still, that means this definition was accepted worldwide for 3-4 years. After many fields develop and try to reestablish their definition for specific for their field. And now after 10 years, basically, international standard organization arrived to the same definition. Now, an important factor in development was that to establish direction and to see the potential of the new field. And that means we have as main goals to change the foundation from micro to nano and create a general purpose technology. And one of the advantages was to work as a most efficient length scale for manufacturing. And certainly this unity of concepts in different fields. After 10 years, we decided to have again a view collecting information from all stakeholders. That means from academics, industry, government, NGOs, and to look again worldwide. And the main purpose was to see was a real progress as compared to 10 years ago. What is a new vision now after 10 years? To redefine nanotechnology from components to systems from in the context for next 10 years. And as I mentioned before, to look how to change the governance, including to institutionalize nanotechnology. And we started by forming a US panel of top experts covering most all the fields that we thought are important. Thereafter, we sent questionnaire all around the world, including in other countries like Latin America, Russia. We have 5 brainstorm meetings. That means we brought people, leading experts, initially in Chicago, in Hamburg with European Union, in Tokyo with Japan, Korea, and Taiwan, in Singapore with Australia, China, India, and other countries. And after we have an overview workshops. That means each time we try to improve the picture. And we have basically input from 35 countries, about 250 leading experts. What is interesting is that we try to have an open source approach, to have continuous input and output, and anything was placed on the web, as you know. This is a group of moderators that when we were around the world, all these people moderated the session, each one in his topic, and tried to obtain the best. You see Chad Mirkin and Mark Hersam as co-chair of the panel, and Daud Bonnell, Jeff Brinkey, Evelyn Hu, Mark Langstrom, Andre Nell, Jeff Welser, Mark Tuominen, Mamadou Diallo, Jim Murday, and Stuart Wolf, each one in his own field. And the report was done on a very fast track. In fact, first workshop was in March, last workshop was on September 30, and now we have the full report ready, edited, and will be published this year by Springer, besides being a government report. And you see, we try to cover the methods from theory to measurements to synthesis. Thereafter, to look to how safe and how sustainable is this. Thereafter, we look to 6 or 7 areas of applications, and to governance, including education and infrastructure. And the basic concept was the following, that in fact was confirmed by this survey, was that in the first 10 years we have a foundational, we cross disciplines and try to develop, to discover a single new phenomenon, a single new structure, and most of the work was empirical. What means is, most of the methods were done by trial and error, and the main goal was to create a library of one-dimensional, two-dimensional, three-dimensional, even motors or patterns on surfaces, but always just as a library of components. In the second part that we see from 2011, 2012, we start now to focus on direct measurements. That means you direct as a scale of atom and time scale of the process, science-based design of material and systems that would allow to create completely new products. And as you see on the right, on the slide here, the focus in the first 10 years was the infrastructure, workforce, and partnerships. Now we move to create new industries and societal impact as a main goal. If you look now to the main focus, one can, if you look backwards, you find that the main contribution in 2000 was to bring fragmented fields in disciplinary fields under a unifying definition and transforming definition, and to have this long-term vision. In 2009, if I use a Lux Research survey in industry, is about $250 billion products worldwide. And this correspond to our initial estimation. In 2000, we made this solid line estimation that by 2015 we'll have $1 trillion products, and 2020 this will correspond to 3 trillion, that is correspond to 25% increase per year. What is maybe surprising for you is that the survey made by Lux Research is almost in the range of few percentage from this line after 9 years. That means you see is a change from basic research without application and application without full understanding to so-called Borg quadrangle and Edison quadrangle to Pasteur approach, where we have science-based methods to solve real problems. If we look to 6 main indicators: number of people involved, number of papers, number of patents, final products in the market, research and development funding, public and private, and venture capital, we find that between 2000 and 2008, we have a rate of increase between 23 and 35%. That means rough about 25, 30%, which is amazing, that is sustainable. That means I will show immediately several curves. That means if we extrapolate this, you find that US has roughly about 40%, but this has decreased in 2009. US was all the time about 40% of workforce, of products, up to 2009 when decreased to about 35%. That means the crisis affected more United States than other countries in average. If you look to investment made by government alone in the last 10 years or so, you see after NNI was announced was an increase in past investments. When we have a second generation of products, industry started to invest more than the government, and at the same time governments have increased their investment, mainly because of investment in new countries like Russia, Middle East, Iran, for instance, and other countries. And at this moment in 2009, we have a flattering mainly in the other countries. In US, because of the stimulus, we have an increase. In Europe, we have an increase of 20%. So the curve is still has an increase in 2009 in government investment, has not decreased. However, what is interesting is that we have a fast and uneven growth per countries. Some countries are evolving much faster, like Korea, China, and others even stable, like Japan, in the last 4 or 5 years. If you look now, each country has a different structure in investing in different fields of science. If you look, for instance, to US here, you find that in materials and chemistry is not a focus. The focus is in life sciences as funding. While if you go to Korea, South Korea, you find the material science has the most focus, and China the same. And so nanotechnology is a larger percentage of the total federal or national funding in those countries as compared to US. If you look now back to this, as I mentioned, curve that was built in 2000, and this was based on looking to changing of penetration of nanotechnology in different products and increasing the total production. And this corresponds about to doubling the final products each 3 years, and also changing in the quality and the content of the products. You see here, I have, in fact, different dots. These are Deutsche Bank, Mitsubishi Research Corporation, Lux Research. Almost all are close, all the major surveying companies are close to this curve. Now, if you look how we take advantage of this, and I use here a report from Lux Research, United States has the most output now from all countries. If you look here, nanotechnology activity and ability to capture the technology is on horizontal line. You see, US has most of the, has the largest outcome. However, other countries have capability to capture better the technology, like South Korea, Taiwan, Japan, Israel. And the problem in the United States in the last 10 years is that we decrease the manufacturing, as the capacity to absorb the new products has decreased. So one has to have a policy to allow development of manufacturing in this context. Now, the main outcomes, if you look backwards in the last 10 years, are, first of all, we have this new phenomena, new processes, and we have a library of one-dimensional up to four-dimensional. Four-dimensional means motors, means three-dimensional plus time, building blocks for devices and systems. And you find a large diversity of so-called components. Other major development is that we have new fields that have grown, like spintronics, plasmonics, metamaterials, carbon nanoelectronics, nanobiomedicine. That means completely new fields. And not only this, we have fields that they develop an intersection with biology, like synthetic biology or system biology, or intersection with computing, like quantum information system. Most important, however, from society point of view, we move from science discovery to technological innovation in 4 or 5 areas like electronics, catalysts, pharmaceutics, advanced materials. We expanded in new areas like energy, bio, agriculture, forestry, and even more we get to develop interfaces with other emerging technologies. As method and tool, just several examples. We start to measure as a time scale of the phenomenon nanoscale, femtoseconds. We start to measure as a sub-nanometer we start to identify the shape of the molecules at the sub-nanometer level. We start to track and to do systematic measurement for single atoms, single molecules, building blocks in nano. We simulate from direct principle domains about 100 times larger. And we start to measure completely new things like negative index of refraction, quantum confinement, nano patterning, teleportation of information between atoms, biointeraction. That means scientifically we start to build a large bed of information. In innovation, I take 2 examples. For instance, spintronics that basically was defined in 2001 as a field has now a lot of devices that I will exemplify immediately with one. And if you look, for instance, for patterning on surfaces, we have now 6 or 7 methods for systematic patterning of large surfaces. To take an example, that means in 2000, the major application of nano was giant magnetoresistance in the hard disk. And we are starting to nanostructure the surface of the hard disk. Now, basically, many components are in phones, in computers, in medical devices, have nano components. I exemplify by 3 developed in the last 2 years. One is this 32 nanometer processor by Intel that makes things run faster. And after 2 storage methods that one, for instance, has a magnetic random access memory that provides a stable conservation of information. For instance, after your computer has a crash, it saves all the information in an instant and maintain it for a long time. And this is a storage for fast memory. Another example of development was that we start to recognize environmental health and safety and ethical legal system as important topics. And we start to build basic understanding from biological principles. We focus on specific nanomaterials. We don't have yet a generic approach. Like any approach, at the beginning, it's empirical, start with most critical areas. And we start to develop some governance principles that were not available 10 years ago. Different risk assessment frameworks, user voluntary codes that, for instance, this was presented less than 1 month ago at Woodrow Wilson. That means each one is a topic on its own. And what is interesting is that we start to develop this infrastructure that it's able to deal with nanotechnology. Something that is very important, the nanotechnology offers probably one of the few transforming solutions for sustainable development, because in other method you take from one place, you move in another place, but in nano you can offer breakthrough solution to have intrinsic savings of energy, water, materials. I take several examples. Nanotechnology already provides about half of the solution in energy-related and water filtration. And this is expected to increase, to be dominant in the next 10 years. There are completely new families of materials that can store hydrogen, can absorb CO2. We have a large range of filtration materials based on nano components, like nanofibers, that are in development and promise to provide a source of clean water worldwide. And in this context, we look to the whole picture, and we found, based on available literature, which are the critical fields and how nanotechnology can address them. For instance, the most critical is biodiversity, as you know. Second is nitrogen cycle. Third, it's carbon contamination and climate change. But one has to look to all of this together. In fact, the critical elements are minerals, water, food, energy, habitat, transportation. I make this point that one has to look as a whole and not to focus only on energy. However, in the report, energy is treated specially as a special chapter concerning the conservation. Concerning applications, we look now that in the last 10 years we moved to active nanostructure, which is happening now, in fact, continues to happen. We move to drug targeted drugs, to sensors with actuators. We created different new kind of transistors. That means we already changed qualitatively. What 10 years ago we were able to do only nanostructure polymers and other passive nanostructures. And what is interesting, we start to advance to a level that we can build a periodic table for these nanomodules or nanostructures that are based on the internal structure of the nanomodules and not on the external characteristics, how it's done now. Several examples, for instance, in medicine. Medical field took 3-4 years to be fully recognized, and after 2004, basically, with National Cancer Institute development, we have a very fast progress. And there are now about 10 commercial products which billion-dollar business, and more than 50 companies developing new cancer targeting drugs at this moment. That means already nano has penetrated as a foundation of medicine and pharmaceutics. And here are several examples. For instance, this is a product by Nanospheres on the top that allows to detect with accuracy about 1 million times better the blood composition, and this can be done in 1 hour in the doctor's office, and can detect even things that were not possible before, even like HIV presence. We have targeted drugs for breast cancer, for prostate cancer, for visualization imaging, and for bone replacement. These are examples of products that you can buy now. Another example of fast development is patterning on surface. It's already this is used in many areas of relevance, and there are new products like deep pen nanolithography, nano imprint. You have this directed self-assembling of block copolymers. Here are just 2 examples. I will not spend the time with the details, but what is interesting, we start to create large-scale surface nano patterning at with economic characteristics. The largest application of nano in the last 10 years is in catalyst. This exceeds nanoelectronics. Here we have, that means, these small structures that are able to cut or assemble different molecules, and the largest application is in oil industry. And in oil industry, we have about $20 to $30 billion catalyst itself, but the impact is about in the range of hundreds of billion if you consider the impact of the process as a whole worldwide. Most of the large companies have adopted this. I mean, this is something that you don't see in the consumer products list. And it's maybe a list that 1 million times larger than all consumer products that you see on the market now. That means if you take consumer product like a tennis racket or cleaning device, that's a minor application of nanotechnology. It's not the dominant. And this is a point that is important. Like many things are hidden in the manufactured products, included on the processes. And I take to show the penetration of nanotechnology that is real in different industry. I look in semiconductor industry, if I look from the point of view feature less than 100 nanometers, about 60% of production now in the United States is under 60 nanometers, about $90 billion products. And if you look to have also a new behavior, that means besides small size, about half of this is about 45 billion. That means you have a specially treated layers to accelerate the speed of electrons, so you have a special nano effect. And by 2020, the consensus will be 100%. That means all electronic industry will depend on nanotechnology. You will not have a competitive product if you don't do this. In catalyst, now in US, you have about, that means in worldwide, in semiconductor that I don't have on this slide, under 100 nanometer is 30%, and US has about half of the production worldwide. That means it's that means the penetration worldwide is a little bit less than in US. However, it's in the same is the same trend. In catalyst is about the same percentage worldwide, 35% roughly, and in has an impact roughly about $35 billion in US. And in pharmaceutics now we have about 15%, and we expect about 50% by 2020. At the same time, new areas, traditional areas like minerals, wood, forestry, other will penetrate. And I take here, for instance, in 2000, you see most of these have zero penetration. Still in classical industry is almost zero now, or zero. But for instance, estimation from industry will be 20% in penetration by 2020. That means you see this horizontal and vertical penetration of nanotechnology. That means overall, if I look in 2010, which are the top 10 products, this is catalyst is the first, transistors and memory devices second, structural applications, coatings, hard materials, chemical, mechanical polishing third, biomedical application, methods to treat cancer and chronic diseases that are in development, most of them, energy storage also most in development, water filtration, video displays, optical lithography, and environmental application. And you see that there are safety concerns to a large group of products like cosmetics, food, etc. And what is most important is that in 2010 we start to have the first fundamentally new products like nanoradio, fluidics, tissue engineering that change the product itself, not only improve an existing product. And we made a balance for the United States overall in 2009. That means federal budget, it's about 1.7 billion. Industry put about 1.9 billion. And we have products surveyed by industry 91 billion, which some goes back to taxes, and about 180,000 jobs with an average cost of production considering $500,000 per job. And that means if we do for the world, we obtain a similar plot which show that the promise of nanotechnology already, even if you are after 10 years, and usually after 10 years you have few inroads in applications, is significant. Now, we created an infrastructure. I will not go on centers. We have more than 100 centers. These are user facilities. That means people can go in different places to develop their own products. You see already a mesh of activities by 5 agencies. If you look to education, mainly NSF done the contribution here, we move education earlier in the pipeline. For instance, in 2002, we moved to undergraduate, high schools, K-12, and technological education. That means now basically we cover all the domains. The critical issue is how we maintain this, because these are not institutionalized programs. They are for 5 years or 2 years or 3 years. If you look for education networks, you find these available centers for universities or for high schools to access nano education. If you look for industry penetration, you find in the United States we have about 5,400 companies in the, if you survey last 15 years or 20 years, that have either a product, either a patent, or either a paper. Not all the companies are active now from this survey here. About half of them have products. Others have only patents and papers, and we have an interest in the topic. You see the clustering Northeast and in California. If you look worldwide, United States still dominates this business aspect. You see that we have more than doubles in Japan or China. However, China came very fast in the last few years. South Korea also came very fast. This was done in average for last 15 years. Now, per year, South Korea exceeded Germany, and China exceeded Japan in last year. That means it's a very dynamic field, and certainly here is a place where you take advantage of the nanotechnology. That means if you look more observational to what happened in the last 10 years, first of all, the viability and societal importance of nanotechnology were confirmed. Initially, it was a doubt for in 2-3 years if this will be developed. We form an international community where this interaction on horizontal, different disciplines, different sectors, different countries, created a lot of creativity, a lot of innovation. Certainly, now we pay attention to safety and ethical issues, especially after 2004, was not in the focus in the first 3 years. After, as it was mentioned before, after the meeting in organized in US in 2004, we have basically an international community. Up to that moment was very isolated. Each activity was personal interaction, but not a framework of collaboration. And certainly, nanotechnology, based on external comments, became a model in developing a long-term approach and governance for an emerging field. Now, let's look, before looking to the future, to see what was realized, what was not realized. If I look to 3 items for each, first of all, I think the biggest in success, in 2000, we told we'll build material by design in 10 years. We couldn't do it because we don't have the science yet. Basically, we don't have the direct measurements, and we couldn't do simulations. And this is one field that remain open to be solved, and I think will be solved. That means if you take a material, we cannot build a function or give a function to build a material on purpose. Now we started only with few polymeric materials to do this on few structures. Another objective that was not realized, initially we told nanotechnology will be ideal for sustainable development. Less materials, less water, less energy, less pollution. This will address many problems. However, if you look worldwide, and including in US, in the first 5 years was a small interest, mainly because my explanation is the main stakeholder, main users, beneficiary, were not organized in these fields. For instance, in water filtration, you have thousands of local organizations that don't have money. In electronic industries, organizations that support this, and you see a product immediately. That means it was longer term. Even was a central problem that I think government should pay attention. This was less developed. Another thing that is less developed than expected is public awareness. public awareness was 20% in first survey, arrived to 30% in 2003, and remained basically the same. What is the reason? Maybe mass media methods were not sufficiently well developed. I think it's an improvement in the last 1 or 2 years, but it's not very obvious. To compare, that means this is a topic that we should address. If you compare with a successful story in Germany, they have less awareness in 2000, and now they have 50% awareness in the public. If you look, what is on target even was doubtful in 2000. The growth rate of the field and this multidisciplinarity that was encouraged by the definition and funding projects created a rate of development of papers and invention about 30% per year, which is much larger than the average increase of papers in other fields. Especially in patents. Patents in average have 30–35% per year. Nanotechnology also stimulated interdisciplinary research and education, and you see now new organization, new way to do work in different departments. And if you look even further, when we speak about funding in 2000, we told that funding for nanotechnology will increase because of moving in depth and moving horizontally and involving industry will increase 30% per year. At that moment, it was very doubtful that will happen. Now, if you look to the track record of the United States, all government and industry is more than 30% per year in the last 9 years. If you look, what is better than expected? In 2000, we thought that industry will be involved after 5–10 years. In fact, what happened is that Nano Business Alliance was formed in 2002, and many companies basically developed groups, at least to survey the field or be involved in 2002, 2003. And things like Moore law that was very doubtful that will continue in 2000 has continued, has even accelerated because of nanotechnology. Other things that is better than expected. We have many new fields of science, some are intersection with other emerging fields, from plasmonics to quantum information system, neuromorphic engineering, that develop and have grown like islands of discoveries. And also the formation of strengths of international community. Now we have a very active community, including in safety. Main lesson that I will call we have learned is that we don't have yet control of the nanoscale, and we need to continue in parallel as we move to innovation, but to continue the pipeline of fundamental discovery and theoretical development. Believe it or not, the main phenomena like quantum, like quantum effects, like self-assembling, like biological interaction are not understood or not simulated yet. And so a focus has to continue. Or if you create now systems, you cannot create systems by random empirical approach, how you create components. You have to move to develop the theory better. Other general comment is that one has to focus equally on emerging fields and also traditional industries, how is textile, agriculture, food, and certainly public-private partnerships are essential. And again, increasing multi-stakeholder and public participation is very important. Now, looking for the future, that means, again, I do not go in details. If you look in 2010, the field is still information, from characterization to synthesis to products. Anything is basically show a rudimentary component that is not at a level of sophistication that is a final mature technology. For instance, in products, most of the products are nano-layers or dispersions. It means it's very simple. Or even all manufacturing processes are empirical. That means we have to move to this to the next phase. In the report, we identify trends, and you find, in fact, in each section a section of opportunities and future trends. But I will summarize several of them. I put on this slide 12 just for limit the focus. First of all, in theory modeling and simulation, I think we'll be able to model 1,000 times faster in 10 years from now. In direct measurements, probably we'll do measurements will increase the brightness of the source for X-ray or other light sources more than 6,000 times. We expect that will accelerate direct measurements in nanoscale and will increase the research. We'll move from passive and active to nanosystem and biosystem. We move to nanosystem self-powered and self-repairing and dynamic as the main characteristics. And now we do not have any of this as a product. And industry will penetrate toward mass use, as we are on the path in catalyst electronics, and we need innovation platforms to cross different fields, especially pre-competitive platforms. Nano EHS has to be for multi-components. Now it's only for one component focus, more predictive, and integrated with a basic research in bio and chemistry, not isolated, how was a tendency in several years ago. Personalized medicine and personalized education will increase. Photonics, electronics, magnetics will be new capabilities that will be integrated. Solar energy will become economic by 1215 in the United States, maybe also in other countries, but just to take an average United States, now it's not economic, as you know, it's more expensive. It's several times than coal burning or gas burning energy conversion. We'll have more and more integration with bio, cognition, information technology, other fields. And we look for integration in educational system. I speak system integration, vertical, horizontal integration, and to institutionalize nanotechnology governance. Now, several examples, what I told. For instance, is the past history, what happened between 2000 and 2010, ability to model different case situation, and this increased about 100 times. Now, by considering the new modeling capabilities and new computer capabilities, we estimate that in the next 10 years will be an improvement of 1,000 times that will allow to do direct modeling and simulation of different structure and devices. If you look to the brightness of the sources that allows to penetrate a smaller scale and smaller structures, the improvement in the last 10 years was 3.6 order of magnitudes. If you compare it to Moore's law, which was 2 order of magnitudes, which is much faster. And in the next 10 years, we expect this to increase other 5,000 times. And this will allow to see direct, for instance, to see collection of atoms a femtosecond or even lower time, and to see in a dynamic context. And so we do not have to wait 3-4 years to make a diagram for a molecule. We can measure in 1 hour. We move, as I mentioned before, to active nano structure, and now we move to nanosystems. We start to have this concept of self-powered and self-adjusting complex systems. And this is just an example, relatively primitive, where we use energy of moving body to mechanical energy day by day in order to power devices in biomedicine, different personalized electronics, etc. In environmental health and safety, I think more and more we move to systematic testing, multi-component hazards, and certainly more and more prediction using the basic science, not based on empirical results. We'll start to create platforms for different products. This is an example. For instance, we start to create sheets of nanotubes, carbon nanotubes, or wires that already have implications from heaters to airplanes to satellites to energy conversion. And the idea is to create platforms that will use the same basic component, the basic element in different industries. And this is already for aeronautics is expected to be implemented in 2-3 years. In satellites already is introduced. And this is something that we'll see like a trend, not only for carbon nanotubes. I should mention carbon nanotubes is one of the tens of thousands of possible important nanostructure in nanotechnology. We spend more time on this because certainly has some special properties, but only because was studied more and what's easier to investigate. There are many other materials, many other composites that are not even explored. That means the field is completely open. Once we move to direct measurements and direct simulation, this will open to many other opportunities. An example in aeronautics, in new planes eventually the good insulation will allow to bring the engine close to the main body of the plane, will allow to replace cables, copper cables with carbon-based cables, will allow to have different sensors to improve the efficiency of the whole aerodynamic efficiency. And basically, this is a plane effectively designed with all the details by NASA and MIT. And this is a first estimation for this plane was it will be about half of the weight, specific weight for Boeing 777, and will have different other improved performances. This is a curve that show the current cost now. It's about 3 to 5 times more for energy. Yes, thank you. And by 2005, 2015, 2016 will become economic to apply solar energy in average in the United States. Now, what are the key areas of focus from science point of view in the next 10 years? Will be integration of knowledge at nanoscale, better experiments and simulation control for better control for self-assembly, quantum behavior, creation of new molecules, understanding of biological processes and nano-bio-interfaces, sustainable development, and certainly governance methods. And one characteristic that for many people will be a surprise, in all these meetings, we expect, based on input from industry and different organizations, we expect an increase of R&D intensity and return in the next 5 years, especially when we move to new method of measurements and new products, fundamentally new products. That means we expect an increase accelerate in the research and development in this interval, and changing more. The drivers will be economics and building completely new systems. That means at this moment the focus is improving an existing product, and many times the curiosity, like sporting equipment. You use nanotubes, for instance, in a tennis racket. However, that is not, it's more, it's a curiosity, it's a driven application, while here will be just economics and fundamentally new applications. Another point is that fundamental research, as I mentioned before, has to continue, and we need focused programs because we have to develop new frontiers and the bottlenecks. The idea is that once we develop some components, we have to stop doing focused research seems not constructive, because now we have to address bottlenecks and to develop completely new fields. And an example of this is to realize by computational design materials and systems. And as I mentioned before, sustainable development is very important. I will go as supporting for this is a survey that we have from industry. You see that more than half of companies by 2011 are interested in nano. These are companies that already have products and plan to introduce nano research and development. If you look at recent studies done by Lux Research for NNI, you find their prediction for increasing interest and production in nano in 2015 will accelerate as compared to previous years. And this confirms this from all sources. In fact, in all countries that we attended, we found these feelings, perception, based on different elements and different information, different developments, that research will accelerate in the next 5 years. Other priorities, I will not go through all of them. It's certainly one, it's to create platforms, system application platform, for instance, for energy, for water filtration, now developing nanoinformatics, and certainly institutionalized nanotechnology. In long term, that means we look nanotechnology to address 4 main general human needs. First of all, knowledge progress. By understanding the nature, understanding the life better, how to treat in medicine, how to, the structure of matter. That means knowledge progress remain, I will call, a main advantage in the next 10 years. So, secondly, it's the material progress. We look to this economic benefit and certainly medical value. Thereafter, we look certainly for sustainable development, international collaboration, the global progress. And certainly, no less, we look how nano will help the quality of life, better dissemination of the technology for equal societal needs. I will call this moral progress. That means in long term, nanotechnology should address also these higher purpose goals. And I would like to close by underlying that we've done this study for 3 reasons. We are closing 10 years of the first long-term vision that has a strong implication in not only in US but worldwide. We look to change in the way in which research is done, which are the goals of research, how the society perceives research, and we have, and the perception we have to prepare for 10 years ahead in order to take advantage of this new technology. I mentioned some things that we try not to go too much further because this could be done, but we done with the purpose of using the existing breakthroughs and science facts to build up to see what can be done 10 years from now, and so to build a solid foundation for people who like to plan research and development and production in this field. I would like to thank you, in fact, for the contribution from international community. My presentation here was more focused on the United States, on the purpose that obviously we are here more interested in what happens in the United States. I like to mention that there are parallel activities, 5 years plan in Japan, and this will be presented on Monday at NSF grantees meeting. It's someone from the cabinet office that will make a presentation of the Japanese program. Thereafter, in Europe, they have other 5 years program in preparation. In China is a 10-year program. In Korea, a 10-year program. That means this international interaction allow us also to bring a kind of common agreement and again a kind of synergies between all these activities. And I would like to close by underlying that science and engineering remains the main source of wealth for society. And nanotechnology is one example how we went from basic curiosity to transforming application in a relatively short time. And some example will be presented next week. As you know, it's Nano NNI Summit in downtown DC. Thank you.
Okay, we have some time for questions. So if you could just raise your hand. We'll get you a microphone because we want to make sure we get it on video. Yep.
Thank you. My name is Noela Invernicia, fellow here at the Woodrow Wilson. Mr. Rocco, you didn't talk a lot about costs, and I wonder if this transition to more sophisticated nanostructures this transition represents a lot of new tools, new productions process, etc. And how is the industry prepared to cope with this cost at this point?
As I tried to underline is that nanotechnology will move more and more to be driven by societal needs and economics. That means, how you explain that in electronics we move to smaller and smaller, more complex structures? I take an example because there it's obvious. Because as you do more sophistication and more basic understanding, you have more performance and overall the economics. That means we expect the phase of spending more money on research without results was in the past, in the last 10 years, because you discover a new phenomenon like interaction of the light with nanoparticle, and you have no result immediately. But now, as you go to more complex, you can do direct measurement, you can understand the behavior and can build a device. That means, maybe to tell in short, so I agree that some research will become more expensive, but the results also will become significantly more important.
Other questions? Yeah, right here.
Bob McCrate, George Washington University. Mike, if this process of governance you see is so critical now, I know you do, how do you estimate you'll handle the strategic implications of nanotechnology in the international environment? That is, for every good application that you've mentioned, all those that are benign and helpful and have societal value, there continues to be a risk for the perversion of nanotechnology, if you will, to weapons development or to new things that pose new unexpected threats to society. How do you expect that governance mechanism may be constructed and may be managed, if at all?
Yes. First of all, I like to mention that the report covers a lot of international activities. As I mentioned, I try to focus on US and this. And I like to make the following point, that development of science and sometimes different developments are natural of a human endeavor to progress. And sometimes each country likes to progress. And so is this one part of the equation. We have all the time in any new development possible negative effects. Could be, for instance, the easiest in my opinion is toxicity of nano component. More complex when you have nano biosystem, or even more complex when you control the DNA and you can create completely new biostructures. And that means this, with all this development, for instance, let's take, before answering to your question, is to take an example from 100 years ago. Pasteur developed the viruses, and anyone could take the virus to put in the water system in a town and kill all the people. It didn't happen. Why? People develop methods to measure, develop kind of method to balance this. That means, I agree, as you go too faster with a car, the risk of an accident is increasing, but you like to take the advantage of the speed of the car. Maybe, so this implies that we have more and more to be very careful about the new development to address the safety and ethical issues as a component of each project from the beginning. And I think this came out in the last 2-3 years that, for instance, nano EHS and ethical issues are essential for the development of technology. Now, if you ask from the point of view of military application, it's a difficult question because most of the countries do not publish any results. United States probably publish more than anyone that I know because we have published NNI results. Most are public, most is for foundation. And so probably has to be an understanding that has to be developed in the future as on diplomatic level, similar how we have for other weapons with large implication. Something specific that a project has proposed is to create an international organization to be funded by different countries for keeping databases, for papers, patents, and something, nomenclature, other things. That means to be an international organization of communication and indirectly collaboration. And this, I think, is needed because it cannot be done by one country. For instance, even now how you have each country develops some nomenclature and it's difficult to agree after the fact or different organization. And so this was a specific proposal, in fact, to address this issue, to create continuing international activity on this.
That we just got one question by email, but I think you started to touch on this. I mean, over the next 10 years, they were asking, do you see regulations developing on an international level, or do you think each country is going to continue to kind of do their own thing in terms of oversight?
As you know, because of the need to have knowledge development together, because no country can develop the knowledge completely alone. And here it's a common interest to develop the knowledge. Also, it's a common interest in trade, in products, in safety of people. I think that regulation will have a tendency to harmonize, to be correlated. I do not think will be international regulation. I think this will be impossible from the practical point of view, but will be a correlation, coordination of these activities more than it is now.
Why don't I take one more question? All the way in the back, yeah.
Malati Srivatsan, I am a AAA Science and Technology Policy Fellow. In your talk, you showed a tendency for China and South Korea to be more and more involved in material manufacturing, whereas US more and more involved in application aspects of it. And if a time comes that we need to depend on other countries for the materials, I think it's all the more important that there is a uniform international standard of manufacturing and characterization established. Are we moving towards that direction?
Well, you ask 2 or 3 questions indirectly. Let's ask to answer to one, and I respond successively. That means, first of all, as you know, standards are not recognized internationally in a compulsory way, are voluntary activities. So, for instance, International Standard Organization is working very hard on this and has different committees. There are other organizations like ASTM in the United States and other 6 or 7, and electronics is another group. That means I think because of the need of trade and the need of collaboration, more and more will be a tendency to have correlated standards and norms. But and I think this is will be because of a practical approach. Now, you mentioned about, first of all, Korea and China have put more money in relatively in their country to materials, but still United States probably is putting more than them in absolute value in those areas. That means just that was a relative value in each country. That means doesn't mean that United States doesn't have activities. And United States at this moment has a lead, as you know, overall. If you look, let's say, in an interval of 5 years, basically in all areas from paper patents. However, The rate after 2006 have increased in United States as compared to the world has decreased like in percentage. Up to 2005, 2006, United States was maintaining the same level, but probably in part because of larger investment in China, Korea, and many other countries, this has decreased. And so United States at this moment has still a large advantage in quality, in citation index, in more sophisticated products. But this is subject of international competition and probably collaboration, and the tendency, especially in production, this is both true for Europe and for Japan, for US, as compared to Asia, is at risk, in fact, in the next 5-10 years, because the manufacturing capabilities, overall manufacturing capabilities, have been reduced, and so it's difficult to produce things if you don't have the components. And so this is a strategic issue that has to be addressed by both Europe and the United States.
Mike, thanks again. I think we got your the presentation on the website. That's okay for people to download. And when can we order this from Amazon?
Yes. First of all the report, it's already on the web, as you know. We have the last typos on this. December 17 will be in print at Springer, and I will make certainly. It's available free on charge on electronic means, and for different, even changes will be maybe a live document, but Springer will print it in end of this year or first part of next year, and will be available as an archival document, yes.
All right. Well, thank you again.